Classical computing has changed the way we live, solving plenty of our everyday problems, although others cannot yet be solved efficiently. Moore's law states that every 2 years the number of transistors in our devices doubles. However, dimensions are now so small that quantum effects are bringing this law to its limit. So why not using this quantum nature of the problem to our advantage? Quantum computing has risen based on the properties of entanglement and superposition. In this context, IBM has taken a pioneering role in this race.
The world of quantum computing still has to define the basic element of its hardware, the equivalent of the transistor. For now, various platforms have been proposed: the spin of a nuclei or of an electron, the excitant state of a trapped ion, or the state of a superconducting circuit are a few examples. In all cases, our information unit, the quantum bit or qubit, has to have two clearly distinguished states, the 0 and the 1, and a way to communicate with the outside. IBM has chosen to rely on transmon superconducting qubits. This circuit approach is based on the resonance of a capacitor-inductor circuit and is made of a linear capacitor and a Josephson junction, kind of a non-linear, non-dissipative inductor created from two weakly coupled pieces of superconductor. The whole thing is built from superconducting materials, like aluminum at cryogenic temperatures, to reduce scattering. Finally, some resonant buses are used for input and output, and others to couple qubits with each other. For instance, the processor used to simulate the beryllium hydride molecule looks like this, with 5 qubits, blue, 2 coupling resonators in green, and 5 in-out resonators painted in gray.
Something special about IBM is that not only are they contributing to the progress of quantum computing, but they are making it available to everyone through the cloud, no matter where or when. They have developed two interfaces, the Circuit Composer and the Quantum Information Software Kit, or QISKit. The Circuit Composer offers a visual and intuitive tool, where quantum gates are provided like building blocks to fabricate your own quantum circuits. Of course, for complicated circuits, adding gates manually one by one is not ideal. Here is where QISKit comes in extremely handy. This is an interface that allows software development in the cloud. There are 4 QISKit elements: Terra, Aqua, Air, and Ignis. QISKit Terra allows to work at a machine code level, so that software can be more adapted to hardware. On the other hand, Aqua provides an extensible Python library of quantum algorithms, so that users can implement them using Jupyter notebooks and even add their developments. QISKit Air is a high-performance simulator for quantum circuits, which allows to compile the codes and check for any mistakes before sending them to a real device. Finally, Ignis provides tools to deal with noise in quantum systems. IBM has 8 real quantum computers available to the public. These real devices are noisy, so they imply imperfect gates and might suffer the coherence, which will introduce important errors. Of these, we have focused on 3, called Melbourne with 15 qubits, Essex, and Yorktown, both with 5 qubits. Each one of them has a different architecture, with different qubits connected, and as we will see, this will be very important to understand the results.
With the aim of trying IBM's resources, we have used the Circuit Composer and QISKit to implement Grover's algorithm. This quantum algorithm was devised by Love Grover in 1996, and it is useful for finding a specific item within a randomly ordered database of n items, given a Boolean function. This algorithm can be divided into 4 stages. First, the state is prepared as a superposition of different states with the same amplitude. Then, the oracle function of the Grover operator, by means of a phase flip, marks the target, and afterwards the target state's amplitude increases, and the other amplitudes decrease. This procedure can be repeated, and finally, in the measurement stage, the qubits are read and an output is given. It is worth saying that this quantum algorithm provides improvements in speed over classical algorithms. First, Grover's algorithm has been implemented using Circuit Composer. As shown, it is simply dragging the gates from the list to the circuit. We have implemented 2 versions. One of them uses 2 qubits at the entrance, 1 and 2, and a simplest oracle function, whereas the other circuit uses 3 qubits at the entrance, 0, 1, and 2, and a Toffoli gate as oracle. In both cases, 2 qubits are measured, and the possible results are 0, 0, 0, 1, 1, 0, and 1, 1. The oracle is designed so that the most likely result is 1, 1. It is worth saying that the second circuit has also been implemented using qubits 1, 2, and 3, and measuring the qubits 2 and 3, in order to compare the results obtained by different quantum computers. The circuits were first run using the simulator, and the results obtained with it indicated the correct implementation of the algorithm, since the result 1, 1 is measured with a probability of 100%. However, when using the real quantum computers, the result is the same but with some errors. In the case of the simplest circuit, the probability of the target state remains larger than in the more complex circuit.
We have also put Qiskit to test by solving 3SAT, a decision problem that's very famous in theoretical computer science, and it is classed as an NP-complete problem. This is a Boolean satisfiability problem, for which we solve what's called a Boolean formula. A Boolean formula is made of 4 simple components: variables, which can only take values 1, meaning true, or 0, meaning false, and the operators not, and or. Our particular input is this 3-variable Boolean formula, and our goal is to set the 3 variables to a combination of 1 or 0, that is, true or false, so that the whole formula becomes true. This has the possible solutions true, false, true, false, 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 or true, true, false, which is equivalent to 101, 000, or 011 in the way IBM returns results, which is with qubits inverted. We have solved this problem implementing Grover with an oracle included in Aqua, called Logical Expression Oracle, which supports the formulation used. When we perform the simulation, we see that the expected results are obtained, so again, we proceed to send it to a real device. Due to the complexity of the problem and the length of the strings involved in the oracle, only the Melbourne quantum computer is compatible with the problem. The results returned are extremely different from the correct ones. This is associated to the huge amount of gates involved in the circuit, which was of the order of thousands, and surpasses the current limits for quantum computers. Also, it shows that a lot of optimization needs to be done when creating quantum circuits.
What does this optimization involve? From what we've seen, there are 2 key parameters: the number of gates and the processor architecture. Comparing the results obtained in each test, we've seen that as we increase the number of gates and the number of qubits, the error gets bigger. This is because each qubit and each action on it has a certain probability of going wrong. Therefore, it is interesting to reduce as much as possible the number of implemented gates and the number of qubits involved. Also, although IBM offers plenty of gates, not all of them are feasible in the lab. For each device, the user-programmed gates have to be adapted to physically compatible gates. If possible, we should be aware of this when designing the circuit. To further optimize the experiment, we must take into account the connectivity of each processor. For example, Yorktown has only 6 connections of the 10 possible. If we use qubits 0, 1, and 2, Yorktown gives better results than Melbourne and Essex, since these particular qubits are interconnected. We can arrive to the same observation when using the Yorktown quantum computer with the qubits 1, 2, and 3, as 1 and 3 are not connected. This implies that to implement one simple CNOT between qubits 1 and 3, we need an alternative combination of gates, which is the reason why the error increases.
We can say that IBM is doing an amazing job developing and bringing quantum computing to everyone. They have presented the first integrated quantum computer for commercial use, the IBM Q System 1. Also, quantum computing is a very promising tool for many applications, such as chemistry or finance. So, if IBM keeps improving their work and their bet succeeds, getting the scientific community used to their formalism and platform, they could become the reference in this growing world.